Good thing that I just realized that now. All right, before we move on too far. Oh my god เพื่อจะบอกว่าชีวิตช่วงหลังๆนี้วุ่นวายมากนะไม่ไหวแล้ว I have to do one thing or the other I don't know too many things นะหรือแบบเสร็จแล้วบอกให้ sorry guys ไม่ได้อัดเลยวันนี้ my god alright แต่ชีวิตมันวุ่นวายเกินไปนะอาจารย์ว่าช่วงนี้โอเคเดี๋ยวเมื่อกี้นั่ง process ในหัวต้องทำอะไรต่อนี่เสร็จโปรอาจารย์ต้องรีบวิ่งกลับไปมีประชุมตอนเที่ยงอะไรตอนเที่ยง45บ่ายโมงมีประชุมอะไรอะไรนะปล่อย11 ครึ่งไงเนี่ยอาจารย์จะปล่อยแล้วจะเสร็จแล้วเนี่ยจะจบแล้วผู้สู้ไปชั่นเนี่ยเดี๋ยวอาจารย์เดินทางเลยตอนนี้ let's call it done like that that's it conceptually you guys okay all right guys so what we're doing over here is superposition principle and it says whenever you have one or more two or more waves meeting at one point all you need to do just add them all y1 plus y2 plus y3 plus y4 on and on and on and the simplicity of this is just linearity of waves so that's what I just noted on here it's a linear wave properties but now Botan all the waves are linear that's the question that you might be wondering the answer is no all right but in just a normal circumstances they are all linear all right you will get a non-linear waves when you have a wave in some exotic material some special environments on that 1 plus 1 will not be equal to 2 but in general if you have just a regular waves no problem okay but what is interesting when you have this we call this phenomena an interference of waves okay so the conclusion about these 2 pages is the properties of the interference okay that's a property of waves whenever you want to do it mathematically you do the superposition principle okay so it's just you just add those waves together okay so we call this interference but then when you think about it because the displacements of the medium can go up or can go down right so in general if we have the opposite case when the y1 and y2 have the opposite displacements so you might have a cancellation effect okay so on the left it's more like it's constructive because the resultant wave get a higher amplitude okay but on the other hand if your displacement is opposite in direction you get a lower amplitude at the point of interfering so what you have over here is called this a destructive interference all right so those are just the consequence of a simple summation of 2 waves that's it okay all right here this is what we can do mathematically so I'm just going to show you the simplest case now we go back to our beloved sinusoidal waves and everyone knows how to read the waves now okay so everyone still remember this one I hope here we go guys look at this is the first wave let me call it y sub 1 you know the amplitude by reading the a you know the lambda by reading the k just a quick review this one is 2 pi over lambda okay everyone still with me omega this still give you 2 pi f or 2 pi over period okay the combo between the lambda and the t will give you the speed of the wave v equal to f lambda actually let me take a look a little bit okay let me use the blue so everything will be color coded so a the k 2 pi over lambda omega is 2 pi f v equal to f lambda or omega over k see all right so I'll just give you a quick review of what we have been doing in the past weeks all right this is it however the sign in between saying that this wave is traveling in the positive x direction yes okay okay now move on to the next Bojan I have another wave but the same amplitude same wavelength because the same value of k same frequency same omega same direction if you want yeah because it's still traveling to your right okay however it's get translated a little bit because they have different initial phase factor cool all right so that means think about this one is like now I have 2 waves that I can adjust the relative position between them okay all right the easiest way will be Bojan if I set this one to 0 so if I turn that phi to be 0 it means both of these 2 are just on top of each other with me so that's what you see as just a single blue line over here because the green is already on top of that one what will be the net waves Bojan is easy you just add these two together. So this is your resultant wave based on superposition principle. Just y1 plus y2, and you are done. Okay? And because you still have this, I don't know you still remember this or not. Do you remember this identity? When you have the summation of two sine A plus sine B, you can put them in a product. It's going to be 2 cosine of the difference over 2 sine of the addition over 2. All right, okay? So if you can do that, then I can actually take these two and just merge them into a single product form of the waves. Cool. All right, so far so good. All right, so think about this one first. The first case is easy. When you put phi equal to 0, those two waves are exactly the same. So you get the twice as big as the original, the red one. That's your resultant wave. Cool. So this one is fine. But then now you think about it, let me try the case that phi is 180 degree. 180 is half a cycle, right? Half a cycle. So half means if the blue is oscillating in this way, the green will go opposite because it's half a cycle this separated. Okay. So in this case, what do you think will happen? The blue is going up, the green is going down, but they are totally out of sync. Yeah, the summation will give you nothing, right? It's 0. Okay, and look at this. After using that identity back here, when you set phi to be 180 degree, look at this factor in the front. Cosine phi over 2. 180 divided by 2, you get 90. Cosine 90 is 0. That's it. So this is your pretty much, you can think of this one as your resultant amplitude. With me? Yeah, it depends on the value of the phi over 2 here. Okay, so when phi equal to 0 in the first case, you plug in 0 over here, cosine 0 is 1. Perfect. You get the resultant amplitude to be 2a, twice as big. Okay, in the second case, when you set phi equal to 180, you plug in 180 over here divided by 2, you get cosine 90, nothing, 0. And that's it. You get nothing as a result, the red one. And now with this expression, you can do anywhere you like. You can pick your phi to be 60, 80, 75, 120, it doesn't matter. Just plug it into this expression and then you are done. Cool?ง่ายไหม? This is it. Simple. Just mathematics. And if you have calculators, you don't even have to do this identity. You just like, let me punch the calculator. What kind of application of this? Anything close to you that have this kind of application? What do you think? Is there anything that's kind of utilized this interference effects, cancellation effects? Yeah, the noise cancelling headphone exactly just do this. Okay, so in your noise cancelling headphone, what it does is it has like a mini microphone in there to listen to the ambient sound, and the chipset over there just pretty much flip the phase of the wave that incoming at 180 degrees. You shift the phase and then recombine with whatever the ambient sound that coming in. So you are pretty much do that cancellation effect. Okay, so that's all you have to do. But back in the day, the chipset that doing that shifting and the generating the sound wave with the 180 degree phase doesn't process quickly as nowadays. So back in the day when you did this, if you clap your hand, it cannot cancel in time. So you still have some leakage of the sound coming in. But I think nowadays, like because your chipset, processing everything so fast, you can do any pause and everything is still pretty quiet. So it's pretty good. I think Bose was the one that did this first. Okay, and back in the day, the main sale of this one is the people who fly a lot. They kind of like annoyed with the engine sound on the plane. It's like humming noise like all the time. So when they put this on, it's like peaceful, quiet. You can sleep on the plane, on and on. So that was the selling point back in the Bose day. But nowadays it's too quiet. So they have like a tunable level of noise cancellation, right? Because when it's so quiet, you're not aware of environments at all. You get hit by a car without knowing it, It's like so bad. It's too quiet. All right, but meditation might work. All right, anyway. Okay, all right, guys. Now, in reality though, what you did was fine. We can understand it, but who will take care of the phase? Who will measuring the phase? Nobody, right? Like when I say something to you, you're not gonna listening to the phase. You're listening to the sound, the voice, and then you do the wave thing, and then you have to calculate. So it's so hard for you to pick up the phase directly. Usually you have to go through some other quantities. And this is the easiest way that you can think of. Think of it this way, guys. Let's take a look at the path length. So that means you have a source, and the source has to travel to you, right? Okay, so because we are sort of like studying sound, so let's say you have like sound traveling to your ears. And then because you need more than one wave, so it means there must be two trains of sound reaching you at the same time. And then because it's so hard for you to measure the phase directly, but it's easy to measure the distance. Think of it this way: you have a speaker right there, one speaker, and there's another speaker right there. So at your position right now, actually there are two sounds wave reaching you right now at the moment. Okay, so it's easy for you to measure the distance from you to the speaker number one and speaker number two. That makes sense? All right, so let's do that. Let's take the measurement of distance. Let's call it R1 and R2, the distance between you and the source number one and you and the source number two respectively. And then what you need to think about is this: if you somehow standing right in the middle, exactly in the middle, so R1 minus R2 will give you 0, right? There's no distance difference whatsoever. Then you can guess you should have a constructive interference. Does that make sense? Because you're standing right at the center. So the wave that reaches you will look exactly the same at your position. All right. So when you're standing right in the middle, then the wave from the two look exactly the same. So they are in sync. So you have a constructive interference. Does that make sense? And then even move around a little bit. Okay. So one distance will get shorter, the other one will get longer. Okay. So now the longer one will take more time to reach me. The shorter one will take less time. So now the wave that appear to me will now not in sync anymore. Okay, so now you have a little bit of cancellation going on. And if you move around a little bit until the two are perfectly out of sync, you're reaching the perfect cancellation point. And that will be the destructive interference. Does that make sense? And I can move around a little bit. Now it starts to get out of sync a little bit again. And then I might be able to reach another point that is in sync again. So I'll hear the loud noise one more time. And I can move a little bit so it starts to get out of sync a little bit more until eventually it's perfectly opposite. You get a quiet sound one more time. On and on and on. Cool? All right, so that's the key. So it seems like measuring the distance should be able to lead you back to the phase analysis. What should be the difference between the two? Okay? But yeah, distance is easy to measure. So this is some sort of like an experiment that you can test, which it doesn't really make sense much, but I mean, we can do it experimentally. This one, you have a single speaker because you don't want to deal with the two speakers. So you have a single speaker, but then you send the sound into two tubes, all right? One tube and the other one. So the distance from the tube number one, let's say is R1, and the other tube, you can have like another distance, but it's adjustable. So for you to be able to do the experiments, right? You know, play around with the distance difference on and on. All right. But anyway, once the tube reaches your ears, then you can listening to the sound. Like, okay, is it quiet or is it loud, quiet, loud, on and on, depending on this path difference right there. All right, cool. So far, so good. Here comes the question. How can I link the path difference back to the phase? If you can get that, that's it. It's done. How can we go back from the distance to the phase? Distance and phase. Distance and phase. This is easy, guys. Easier than you think. Because everyone knows every one wavelength is the same as the wave has already been traveling for complete one cycle. Does that make sense? So that is our conversion factor here. Every one perfect wavelength equivalent to one perfect cycle. In terms of the angle, that is a complete 2 pi rotation. With me? Right? One wavelength equivalent to the wave has already gone through 2 pi. Okay, so that's it. The unit of the wavelength is meter. The unit of that phase is radian. So this is your conversion factor, guys. Every one wavelength equivalent to 2 pi angle. So that's it. Can you see this now? Let's zoom it in. Zoom it in. Can you get this now? See, this is the path difference. But now you say, but I want the phase, I want the angle. Well, I know that every one wavelength equivalent to 2 pi. So I just multiply by 2 pi for every wavelength that you have gone through. ทุกคนนิ่งผิดปกติ Does this make sense? Okay. So you just have a factor of 2 pi over lambda multiplied by the delta R. But the way that, I don't know, Thai student did this is the เทียบบัญญัติไตรยาง Have you heard of this one? That is no wonder no one, because I haven't heard of this one for a long time. But have you heard of เทียบบัญญัติไตรยาง Anyone? Yes. Yeah. Do you know this word in English? เทียบบัญญัติไตรยาง I don't know who built this word. เทียบบัญญัติไตรยาง Okay. All right. For those of you that has heard of it, it will look like this. It goes like every one lambda means 2 pi. If you want delta R, how much is it? And then what you did was multiply this divided by that. So you get 2 pi delta R over lambda. That's called เทียบบัญญัติไตรยาง This happens like 25 years ago or something. All right. But I have been searching for this in textbook. That's never happened. I haven't seen this เทียบบัญญัติไตรยาง anywhere in any, I don't know, international textbook or whatever. So I don't know who did this. But internationally, what they do is just a ratio. There's nothing more to it. Okay, so what they do is it's just a ratio, right? It's just comparing the ratio, because you know that, hey, 2 pi for every lambda, right? That's the factor that we know. So you want to know what should be the phi for the delta R. So you do the comparison just like what we did with like P1 over T1 equal to P2 over, same thing. So you know that, hey, the factor of 2 pi for every wavelength lambda must be equal to what? Oh, I do the opposite. Sorry, guys. It must be equal to the phase for every distance that you would like to calculate. That's what it is. Just comparing the ratio. That's all. And then you just move delta R to the left, and then you get the value of the phi associated with the distance delta R. Okay, cool. All right. Okay, so about 50%. Yeah. So half of you have heard of เทียบบัญญัติไตรยาง So for those of you that have heard of this, understand what I'm doing over here, right? But for those that haven't heard, that's okay, perfectly fine. Don't worry about it. I just wondering, like, has anyone that's gone through like international school and studied เทียบบัญญัติไตรยาง How do they call it in English? That's what I want to ask. เทียบบัญญัติไตรยาง Comparing บัญญัติ What is บัญญัติ? It's like บัญญัติ and it's a ไตรยาง thing too. It's like it's a triple something. You know, you have to do like, yeah, I don't know. Forget about it. All right, guys. So that's it. So this is the formula. You think of it. Don't think of this as a formula. Think of this one as a units conversion. You want to convert meter into phase, and your conversion factor is just 2 pi per one wavelength. That's it. Okay. So it's not like a formula per se. All right. And with that, then here we go, guys. This is what you can think of. Hey, if you have the delta R to be perfectly multiple of lambda, you get a constructive interference. Do you with me with this? With me? Okay, so let me standing right in the middle again between two speakers. All right, right here, delta R is 0, right? Because R1 and R2 are exactly the same. So there's no phase difference, there's no path difference. So everything looks exactly the same to me. Two waves are in sync. Perfect. Okay. Now I move away, it starts to get out of sync. Okay, completely out of sync. And then I come back to the way that it's sync again. So if I be able to get back to this, it means the distance from one speaker relative to the other must be separated by perfect one wavelength now. Because everything looks exactly the same again. With me? All right, and if I move away a little bit more, it starts to get out of sync, perfectly out of sync, and in sync again. So it means now I got the second shot of hearing a loud sound. So that means the distance coming from one must be 2 wavelengths away from the other now. Okay, and I keep doing the loud again. So now it's going to be 3 wavelengths relative to the other. So every time that I hit a multiple of wavelengths of the path difference, I get one perfect constructive interference, on and on. So that's why this is the condition for the constructive interference. Every time that the delta R is multiple of wavelength, that's when you hear a loud noise, loud sound. Okay, and of course you can do now the opposite, but if you want destructive interference instead, so you can just move around, and then eventually you hit the out of sync condition. To get to the out of sync, the 2 waves must be half a cycle away. With me, half a cycle to make the phase 180 degrees apart. With me? So half a cycle, here we go. That means half a wavelength. Okay? All right. And then you keep moving until it's out of sync again. So you just add an extra lambda to this. With me? So the first hit that you're going to hear nothing is lambda over 2. But the next hit, the second time that you're going to see a quiet sound again, when you move away from the first hit by another wavelength. So the next time that you're going to get nothing is, okay, let me write it out. First time, number 1 is when it's lambda over 2 apart. The second one will be 3 lambda over 2. You add extra lambda to it with me. And then the third time that you're hearing this is 5 lambda over 2, on and on. So whenever you have an odd number, 1, 3, 5, you represent it with this notation over here, 2n plus or minus 1, depending on what you like. Okay, so if you pick plus over here, it means n start from 0. However, some of you might prefer, like, can I do 2n minus 1? That's fine. Then you start the numbering by n equal to 1. Cool. Nice. All right. So that is it. เฮ้ยแต่บอกวันนี้มันง่ายมากนะ superposition principle มีแค่นี้จริงๆนะ All right, but before we dive into it, do you want to try the actual experiments? I think I can do it, and that will sink into your head much better. So I will have the frequency generator. Here we go, guys. For those of you that do a lot of music, I will give you, here we go. Let's do the actual calculation, guys. Ma. All right, those are 2 speakers right there. You're sitting over here. What should be about the distance right now from you to the speakers, let's say? All right, so this is going to be fun, or maybe it's going to be a disaster. All right, guys, so you're standing right here. You have 2 speakers. There you go. All right. Okay. And your distance, let's say, at roughly, let's say 5 meters. Is that about right? 5 meters. Okay, cool. 5 meters. 5 meters. Not lambda, sorry. R is 5 meters. Okay, something is wrong with my writing over here. Okay, 5 meters. Approximately 5 meters. Okay. All right, and your friends may be a little bit like 2 seats apart from you, might have delta R about 1 meter, let's say. So that dude over here will sit here. You guys with me with this? Yeah. All right. So those of you that's sitting in the center is about 5 meters away from the speaker. For those of you that not sitting at the center, you have a different of the path, right? R1 and R2. All right. So let's say for this guy, delta R is, let's say, about 1 meter, maybe, approximately. Okay. Now, if I want this, okay, the guy sitting here to hear no sound. No sound. What should be the frequency of sound that I hit, or what should be the frequency of sound that I supposed to send out? เข้าใจคำถามได้ไหม If I want this guy to have no sound at all, so that means the first time that you're going to hear this is when phi, according to this here, this condition over here, that means I requiring the destructive interference, right? For the first time, so that means because the delta R is 1, so the phase difference, here we go. Actually, I don't need to refer to the phase anymore if I don't want to. Okay. All right, guys, so let's do this. So the delta R is going to be 2n minus 1. And then what you can do is just take the lambda over 2. And because you are seeing this for the first time, you can set this n equal to 1. You guys with me? Okay. Or, I mean, saying that you just have to take 1 meter to be equal to lambda over 2. Okay. So that your friends next to you will start hearing no sound. Okay, conclusion. Okay, with me. All right, so far from this, I set this to be the first time that this guy hearing no sound. So that means the lambda has to be 2 meter. Okay, so let me write like this, 1 equal to lambda over 2. So lambda is 2 meter. So let's take the speed of sound to be approximately 350, just like what we saw before. So what should be the frequency, guys? So V equal to F lambda. So F equal to V over lambda, and that will be 350 over 2 meters. So it's about 175 hertz or so. All right, guys. I am going to send out 175 hertz to the speakers right now. Lord, man. And those of you that sitting in the middle should hear loud sound. And those that sitting like a meter apart from you or so approximately will hear nothing. Well, low, quieter sound. All right, this is 175 hertz, guys. Yeah, it's coming out of this. You have to move your head around a little bit. No. Can you feel the difference in amplitude a bit? So it's going to be loud someplace and it's going to be quiet somewhere. Can you see that? Can you move around a little bit? Yeah. 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 Okay, maybe this number is a little bit too large, or John is 1 meter. It's kind of like way much. Okay, so let me play around. I'm gonna send it out a higher frequency. So now you don't have to move your head too much because now you're gonna get like constructive, destructive, constructive faster. So I'm gonna, okay, let me stop this. Let me do like a super, well, not super, but let's do 1,000 hertz. Why not? It's still quite okay. 1,000 hertz will sound like this. Can you feel that? Can you feel wheel หน่อยได้ไหมมันจะwheel หน่อยไหม คนอื่นเขามาดูห้องเราเขาบอกว่าห้องนี้มันทำบ้าเลยเนี่ย But you feel right? There is like a different in amplitude, right? When you move your heads around, like it's kind of like there is like not very symmetric sound between left and right ears that you're hearing. That's what it is. Some side is constructive, the other one is more destructive, on and on, right? Even though it's not perfect here because maybe the speakers here, it's not, well, it's not a point source and the frequency that coming out has some noise on it, but at least you see there's a quieter sound and louder sound going alternatively throughout the space. Okay, cool. All right, so that's what it is. You can play around with this if you like. But yeah, it's kind of fun to do. But I think 1,000 hertz already hurting my ears. So, all right. I think maybe 600 seems to be okay. Ah. Yeah, I think that's, if you walk around, it's going to be much better. All right, guys. So I hope you see my points over here. All right, but that's what things that you can do with that simple calculation. All right, so let's look at one exercise over here. Then we take a break. Sounds like a good plan. Okay, so look at this one. You have two traveling sinusoidal waves are described by the wave functions below. All right, so good thing about whatever you are seeing right now is good in the sense that everyone will be able to read the wave function now. Everyone knows how to read it out, right? You know all the aspects of waves by just reading out. Cool. So what is the amplitude of the resultant wave? And what is the frequency of the resultant wave? See, they're just asking a very simple question. Well, hey, find me the summation of the two and read out. Okay, give it a shot. Everyone now knows. Let me write it like this. The total wave that you're going to get after the interference is just simply y1 plus y2 from superposition principle. Okay, and then what you do is just add them, guys. 4 pi x minus 12 pi t. All right, that's just a regular t, guys, not tau. Not tau, sorry. Yeah, that's just a regular t. Okay, plus 5 sine. Wow, but look at it. It's the same k, same traveling direction because of the negative sign, same omega because there's the same number in front of t. Only phase has been shifted by pi over 4. Can you see this? See? All right. So everyone knows how to read this one now. But now we have the case that you have two exact waves form, look exactly the same, traveling in the same direction, and they're just separated by a little bit, and then it's just going to interfere. And that's it. What you can do is just refer to that identity that we have before. It's just summing the two and just make it look compact. Okay, so it's just going to be 2 times whatever you have. Okay, I have a common factor 5. Let me put 5 out first. I have cosine of the difference over 2. So I just take the cosine, do the difference. So I get pi over 4 divided by 2. You guys with me here? Okay, according to that identity. Okay, I get the cosine of the difference. So when I have the difference, that 4 pi x minus 12 pi t just cancel, disappear. And then divided by 2. Okay, followed by the sine of the sum over 2. So you just have to add this with this and then divided by 2. Okay, so let me highlight over here. This is a minus b over 2. So what I'm doing over here is a plus b over 2. Okay, for the sine terms. So what you have here is, that is just the sum divided by 2. What you have left is just going to be exactly the same, 4 pi x minus 12 pi t. But then divided, subtracting by the pi over 8. And in terms of the final waveform or wave function, this is it. All right, you have already applied the superposition principle and you're done. This is good, all set. But part A, they're asking for the amplitude of the resultant wave. But what is the resultant wave amplitude? You just want the amplitude. We already said whatever shows up in front of sine, that is your amplitude. With me? Okay, because we know sine function never give you anything bigger than 1, never give you anything lower than -1. So whatever the numbers that shows up in the front, that is the value of the amplitude. So that's it, guys. Your amplitude is 10 cosine pi over 8. Done. That's part A. Now, what about part B, guys? What is the frequency of the resultant wave? This is easy because we know how to read waves now. Look at this. The amplitude is done. Look at this. Look at this. Everyone knows how to read this because this, oops, sorry. This is K, factor in front of X. Numbers in front of T, that's omega. This gives you the direction of movements, yeah? So what you have here is, omega is 12 pi. See, you just do the same reading of the wave function, just like what you did before. And then you just equate this to 2 pi f because they're asking for the frequency. If they are asking for angular frequency, you will answer 12 pi and you're done. But because right now they want just the frequency, so f is just 6 hertz. Done. Okay, อันนี้ง่ายเกินไปไหมพูดถึงง่ายเกินไปข้อสอบเป็นไงมั่ง Not good. I thought like second page everyone looks okay หน้าหลังเหมือนจะดูดีนะแต่หน้าแรกเหมือนบอกว่า tricky ไปหน่อยปะ tricky ทั้งสองหน้า เอาละยังครูไหมอ๋อโอเค I thought I tried to make it straightforward all right guys oh shoot okay I'll try to do better second time นี่เดี๋ยวนี้มาแปลกว่านะโลกยุคไหนเนี่ยนะเดี๋ยวอาจารย์จะทำดีกว่านี้นะพวกเราทุกคนเดี๋ยวสอบครั้งต่อไปอาจารย์จะตั้งใจให้ออกข้อสอบมากกว่านี้ All right guys take a break right here take 10 and then we'll continue with the interference of waves all right all right so this one will look exactly อีกแล้วกันไม่กล้าพูดแล้ว exactly like question in the exam ชักไม่ค่อยเหมือนแล้วหลังๆแต่I'll try to do better guys I'll try to do more like copy and paste more แปะมาจาก handout okay all right guys try this you have a pair of speakers okay just like the scenario that we just did and it's 3 meters apart this is just the experiment we did all right and let's say you have a person listening originally at point O which is at the middle at the center right and now the listener then walks to point P so he walks up a little bit which is a perpendicular the distance of 0.35 meter from point O before reaching the first minimum so what is the frequency of the oscillation this is exactly what we did in class but just translate it into a problem in the text มาพวกเราทำได้เลย maybe the annoyance part is just number crunching problem because it's trigonometric you know it's like a Pythagorean theorem that needs to be done here but it's not hard all right but take a look at this one for those of you that don't see this clearly this might help all right this is a scenario that we just had you are standing at point O and he says hey this is at the center so you are guaranteed that you're going to hear a constructive interference right it's going to be a loud sound here at point O okay because you are standing right in the middle the wave from two speakers look exactly the same to you okay now you walk away a little bit so it starts to get out of sync and the information that you have was just saying that once you have reached point P you hear no sound that's your first minimum okay so at this point that is your first destructive interference with me so with this information is just saying that at this point the delta R is exactly half a wavelength with me guys yeah all right and just to sort of like extrapolate from this I think this is kind of nice so what you have over here is the scenario that we just had if I just keep walking I will reach another point let's call it Q this is going to be a constructive interference and if I keep walking up it will be a destructive interference again and if I keep walking up it will be constructive again on and on and on you guys with me with this okay and you also know that at point P is lambda over 2 path difference once you reach the next maximum sound that is exactly 1 wavelength with me and once you move up again you hear the second minimum that is going to be lambda over 2 and another